Hello, Royals. Today we are going to talk about how to use factored form of polynomial functions. We're going to start by going all the way back to grade 9 and thinking about linear functions. But we're going to do so through a bit of a different lens. We should be pretty familiar with this function from grade 9. It's a grade 9 student would probably say it's a line with a y-intercept of -3 and a slope of 1. We might want to try looking at it as a polynomial function of degree 1 with a positive leading coefficient. So our like quick sketch here, we would use the positive leading coefficient to tell us that it's got right positive end behavior. And the fact that the degree is odd tells us that we have opposite end behavior. I mean, like we know that it's going to be a line in between there. Today, what I want you to start thinking about is, instead of thinking of this as a line that has been shifted down 3 and has a y-intercept of 3, I want you to just do this right there. A couple of students have asked me about this, about transformations of linear relations. If you just draw brackets around here, which you're allowed to do, it kind of forces you to think about this subtraction of 3 as being a horizontal shift right 3. See, we don't care too much. We haven't cared too much about the y-intercept for these curves. We're more interested in the x-intercept. This curve has one x-intercept. Its one x-intercept is a linear or single order or order 1 x-intercept, and it occurs at 3. The x-intercept comes from the root of the factor. Okay. Do not memorize. It's just the opposite of that number right there. That is going to cause problems quite soon. Okay. In fact, right away, if I say, let's just consider, so our directions are going to be to sketch these curves. If I give you, say, f of x equals, say, 2x minus 3, and we want to treat it in sort of a factored form, you'll kind of notice, just like with k values, that to spot the root of this factor, this isn't going to have an x-intercept of 3 anymore. We could remove a factor of 2 and then spot the root, or we should be able to notice that the root of this factor occurs when 2x minus 3 is equal to 0. Here's why there's a reversal in the direction, and here's why we have to have it in a factored form. So we sketch a degree 1 polynomial function with a positive leading coefficient, right positive end behavior, odd degree, so opposite end behavior, with only one x-intercept, a linear x-intercept, where you'll change sign across there, or you look like a line near the x-intercept of 3/2. And I'm going to use my old Zoom cheat, I suppose, and say wherever I draw it, that's what I'm going to call 3/2. We'll label the y-intercepts a little later here. You can always find a y-intercept. Now is later, I guess. You can always label it, find a y-intercept by evaluating f of 0. F of 0 is going to be -3 here. So wherever my curve crosses the y-axis, I'll label -3. For this function, f of 0 is also -3. So I'll label that -3. And I am allowed to do this. I don't need the scale on my x-axis to be the same as my y-axis. Don't forget to label your functions. Okay. Now let's move to grade 10. There we go. And look at a function in factored form like x minus 3 times x plus 5. Okay. Through an advanced functions lens, we should look at this curve as a curve that has the positive leading coefficient. Without expanding, I should be able to see that my coefficient is going to be 1 times 1 times 1 out front. So that's a positive 1, right? Positive end behavior. And without expanding, I should be able to predict that with these exponents of 1 and those exponents of 1, that my highest exponent in expanded form is going to be 2. So this is a degree 2 polynomial function. Even degreed functions have similar end behavior. Not a surprise, the direction that the curve is going to be going in. This curve is going to have two x-intercepts. My x-intercepts are going to be the roots of these factors. My x-intercepts are going to be 3 and -5. Again, I'm not just memorizing, it's the opposite of that sign. I'm thinking what number would make this factor 0. The number that would make this factor 0 is -5. So I'm going to put an x-intercept at -5, and an x-intercept at +3. Now, these are two linear or single order x-intercepts, which means that close to the x-intercept, the curve does behave like a line in the way that, like, I cross the x-intercept. I change sign as I cross x equals 3, and my function changes from being positive to negative as I cross -5. Excuse me. Now, I knew I guess I could use grade 10 knowledge to say the direction of opening is up. I used my positive leading coefficient to determine the right positive end behavior, and the even exponent, the even degree, to determine the similar end behavior. But I can also check my sketch by calculating the y-intercept. F of 0 here is going to be, no need to expand to find my c value. It's going to be 0 minus 3 times 0 plus 5, or -15. And I'm going to label this right here. I shouldn't be turning before then. That right there, wherever I cross, -15. And I'm going to label my function. And there's a decent sketch of this curve through a polynomial lens. Okay, we're going to deal with more complicated examples tomorrow, but I want to give you an example of some reversals that cause problems for students that are memorizing a little bit too much. Here, let's try something like 2 times 5 minus x times x minus 3. So students that memorize too much and not the right thing will sometimes say that this curve has an x-intercept of -2 because it's the opposite of that number, and -5 because it's the opposite of that number, and then +3. Well, they get like 1 out of 3 or 2, right, I suppose. Now, this curve, if I think about the leading positive coefficient without having to expand, notice to get the x squared term, I would have -1x times +1x times 2. So I can predict without expanding that I have a leading coefficient of -2. The leading coefficient is not always going to lead. This is not perhaps the standardized factored form, but it is a factored form. I could catch any mistake I make here with my y-intercept if I like. But let's try it from this format. With a leading coefficient that is negative, I'm going to have right negative end behavior. Because my degree is 2, which is an even number, I'm going to have similar end behavior. I then sketch a curve that has x-intercepts at the roots of these factors. My x-intercepts are the values of x that make y equal 0. And if f of x is going to be 0, that can occur when 2 is 0. Well, guess what? 2 isn't 0. And there's no value of x that will make 2 0. Or when 5 minus x is equal to 0. And that happens adding x to both sides when x is 5, not -5. And when x minus 3 is equal to 0. Okay, so you have a method for determining the x-intercepts that does not use memorization, which means you wouldn't forget it and accidentally write the wrong number. I'm going to regret my choice to center on the origin here. Let's scribble this out a little bit. All the way, actually. And sketch a curve so that we can see x-intercepts of, I'll put 3 about there, and I'll put 5 about there, I guess. Okay. Then I draw a curve that has right negative end behavior and similar end behavior. It's going to look a little something like this. I'm going to try my best to keep it always curving. The curve more or draw less becomes problematic when you're expected to label the y-intercept here, because I'm having a hard time. That's about the best it's going to be. Maybe I should be using a pencil. Label that. And to double check my direction, if I had accidentally thought that this had opened up, I would have caught that when I find my y-intercept by doing f of 0, which is going to be 2 times 5 minus 0 times 0 minus 3, or what's that, 10, -30. So yeah, my y-intercept is negative. I'd be surprised if I thought my y-intercept was supposed to be positive. That should all be review. There's still a couple more pieces of review here while we get used to factored form. Let's look at f of x equals x minus 3, all squared. A degree 2 polynomial function with a positive leading coefficient. As an advanced functions student, I say because the leading coefficient is positive, I have right positive end behavior. Because the exponent is even, I have similar end behavior. But this degree 2 polynomial function, which could have 0, 1, or 2 x-intercepts, this one has only one x-intercept. Now, all of the curves above with exponents of 1 on the factors that cause the x-intercepts, they behaved like linear relations. If you zoom in, I don't want to zoom because it'll ruin my focus. If you zoom in there, it's going to look linear, like it's crossing the x-axis just like a line would. But this curve, close to x equals 3, is going to look like a quadratic. That might sound silly because the function is quadratic. But I can like find regions where the relationship might look sort of linear, but right here, the relationship looks quadratic to me. We have what we call, not a, I should have labeled this, not a single root or an order 1 root, but a double or linear root. A double root or an order 2 x-intercept or root if you like. X-intercept, don't call it a degree 2 root because we save the word degree for the function itself. I'll show you that later. Or a quadratic root. I haven't done many examples with leading negatives. If we just throw in a leading negative, students asked about vertical reflections. You could think of this curve being vertically reflected. But again, I think it's best if you were just to like analyze its end behavior differently. Okay, now let's take a look at a cubic in factored form. Let's consider f of x equals x plus 5 times x minus 3 times x minus 4. I can see that this is going to be a cubic if I expand it. I mean, it is a cubic right now because the sum of my exponents of all the powers is going to be 3. Or if I were to distribute all of the terms, I can see that there is going to be a positive 1x cubed here, but I don't want to distribute. I don't want this in standard form. Factored form is by far more desirable here. Okay, so I know that my degree is 3 and that my leading coefficient is positive 1. We start with the leading coefficient. With a positive leading coefficient, we're going to have right positive end behavior. And with an odd exponent, we're going to have opposite end behavior. Okay. Now I can label my x-intercepts, and degree 3 polynomial functions can have 1 or 2 or 3 x-intercepts. This function, with 3 factors that have 3 different roots, is going to have 3 different x-intercepts, 3 linear x-intercepts, 3 degree 1, or sorry, order 1 x-intercepts. See, this is a degree 3 polynomial function. You don't want to start talking about degree 3 versus degree 1. Degree 3 polynomial function with order 1 roots, or roots of the first order. That sounds like they're in Game of Thrones or something. Yeah. So what we're going to do is we're going to try our best to draw a smooth curve. Now, my x-axis, I said I don't care that much about scale. My x-axis, I try to keep roughly to scale. Like -5 has to be to the left of the y-axis. Positive 3 needs to be the right of the axis. Positive 4 needs to be the right of the of positive 3. But you should not go -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. You don't need that level of accuracy at all. So it might bug you that maybe that's a little bit too far. Well, too bad. If they're too close, it's going to be hard to draw the curve. What we're looking for, what advanced functions teachers are looking for, is appropriate curvature. Now, all of these are linear roots, so notice I'm kind of taking my time here turning, and I'm coming down almost directly on top of 3. I sort of feel here that I might need to slow down and start curving around to get through that 4. Not too bad. Curve more, draw less. Right. Now, I've gone ahead and I've made a common mistake, which is, maybe I didn't. Often students feel like, I think just by default or by accident, they draw the curve turning on the y-axis. And that's not going to be the case. Imagine we exaggerate this and make that like plus 55 kind of thing. Or maybe if I had done this to scale, -5, 4, 3, 2, 1, 0, 1, 2, 3, 4. If I draw a smooth curve first, and then figure out where the y-axis would have been. -5, -4, -3, -2, -1, 0, right there. Well, you can still see mine almost looks like it still turns on there. Anyways, yeah, don't maybe ignore your y-axis when you're drawing your smooth curve. Okay. You're definitely ignoring your y-intercept. I don't think calculating your y-intercept first is a good idea, because you'll want to, you'll put it on your axis somewhere, and that's going to affect where you draw your curve. Draw your smooth curve, label it, check your curvature, and then your checking of the y-intercept when asked to label all y-intercepts is like a final check to make sure that your end behavior is correct here. F of 0 in this case is going to be 5 times -3 times -4. And don't let the size of this number change your sketch at all. This is going to be, let's see, 12 times 5 is 60, or 15 times 4 is 60, or 20 times 3 is 60. And that right there is 60, because I say so. Changes to the value of the leading coefficient. Here, let's just recycle this question. What if we did put a 2 in front of there? Then my y-intercept is just going to be twice as large, and I would just switch this to 160. It's going to be a steeper curve and further from the, twice as far from the x-axis as the original, but my sketch doesn't need to change. If the leading coefficient were negative, well, then that kind of changes everything, doesn't it? Let's just switch the numbers around and try one like -2 times, oh, this one's a little different, x minus 1 times x plus 2. Another degree 3 polynomial function with 3 linear roots. Those are the factors that contribute to roots, each of them having an exponent of 1 on it. Again, the students that memorize a little too hard will sometimes think that +2 is a root, because it's just the opposite of that. Your roots, or your x-intercepts here, can occur when, let's concentrate on the two more obvious ones, x minus 1 is equal to 0, or x plus 2 is equal to 0. Now you could say, or -2 times x is equal to 0. But the factor of -2 does not contribute to a root. If you accidentally think that you have a factor of -2x out front, I mean, that's not wrong. When you solve, when you isolate for x in that factor, you'll still get that you have a root of 0. When you have an isolated factor of x, it causes an x-intercept of 0. That's going to make the y-intercept less useful on this curve. So we really need to pay attention to our end behavior, or I can show you some strategies in the next unit that help us avoid problems there. I'm going to scan my intercepts and decide to maybe skew it a little bit to the left here. I draw a curve that has an x-intercept of -2 and +1 and 0. And if I have an x-intercept of 0, I definitely have a y-intercept of 0. Degree is 3, leading coefficient is negative, right negative end behavior, opposite end behavior, and then I can start drawing. Let's just get this smooth curvature in here, down through there. Well, here's a great example of not turning on the y-axis. Reason why you shouldn't, by default, turn on the y-axis. You're definitely not turning on the y-axis here. Okay. Notice the y-intercept, f of 0 is going to be 0. -2 times 0 times anything is going to be 0. So it doesn't really give me a hint about where the function exists. Also pay attention to the fact that we have sketched, what, 1, 2, 3, 4, 5, 6, 7, at least 7 functions so far, using 0 tables of values. Using a table of values here is way too slow. You will not have the time or the space to use a table of values to draw a sketch. It demonstrates a lack of understanding of the principles of polynomial functions if you feel like you need to use a table of values. Sometimes students say, well, I just wanted to check. You shouldn't have to. Okay. Okay, let's mix things up a little bit. Still keeping it the same degree, but let's watch what happens when we do something like this. Without expanding, I can predict that this is going to be a degree 3 polynomial function, because I'll have an x squared multiplied by an x, giving me an x cubed. The sum of all of my exponents on x, 2 plus 1, is going to be 3. I have a degree 3 polynomial function. My leading coefficient is still just +1 in this case. I don't know, let's just change the number to, there we go. My leading coefficient is +4. I don't really care about it being 4. I care about it being positive. So I get ready to sketch a polynomial function that has a positive leading coefficient, right? Positive end behavior, with an odd exponent, so opposite end behavior, but only two different x-intercepts. An x-intercept at -5 and an x-intercept of +3. Yeah, maybe closer to there. Kind of thing. Now, this curve and the curve above it had linear x-intercepts. The curve looks like a line as you cross the x-intercepts. Because of the odd exponent on that factor, the factor changes sign as you cross those roots. Here, my curve is going to look quadratic near 5. I'm not going to sketch y equals x plus 5 squared up there because the signs of this factor also have an effect. I need to use what I know about the end behaviors to make sure that I'm in the right location. But what I'm going to do is I'm going to touch the x-axis at -5, but I'm not going to cross the x-axis. I don't always cross the x-axis at x-intercepts. And because of that, because I want to bounce off and have appropriate curvature, I should not be aiming for -5. You want to aim a little bit to the left so that you have room to turn nicely, like a quadratic. And if I feel like I missed -5 a little bit, I have the power to just move -5 a bit. At 3, I'm going to cross the x-axis, just like a line. So I'm going to take my time and turn. I'm trying real hard not to turn on the y-axis accidentally. But notice how I just sort of approach 3 almost from below and cross like that. And get a nice smooth curve. Okay. We have an order 2 root, or a quadratic root, and an order 1 root, or a linear root. And that'll help us predict the behaviors of curves. This is, in our course, one of the only times that we'll be able to figure out a local maximum when it happens on the x-axis. This curve has a local maximum of 0. We will not be able to predict the local minimum. It does not happen halfway between -5 and 3. It happens in between -5 and 3 for sure. And I mean, if you wanted to, you could use trial and error and just substitute in a lot of numbers, but that's not a strategy we use in advanced functions. We wait until calculus to figure out exactly where that point is. Okay, I'm going to speed it up a little bit, because we should be becoming faster and more efficient here. Oh, y-intercept, sorry. F of 0 is going to be 4 times 5 squared times -3. That's 25, 100, -300. Guess what, buddy? You are -300 because I say so. Can you imagine drawing this to scale? Like you saw this on Desmos in class probably. That like you go over 3 and then you need to go down 300. That would be so steep that I couldn't possibly demonstrate my understanding of curvature. Stretch your scale, not your curve. If we had 4 times, or here, let's switch it to -4 times x plus 5 times x minus 3 squared. This curve shares a lot of properties with the curve above. They're both polynomial. They're both degree 3. They both have x-intercepts of -5 and +3. They're different in that one has a positive leading coefficient, the other has a negative, so their end behaviors are going to be opposites. Because it's an odd degree polynomial function, it has opposite end behavior. And then the order of your roots is going to be a little bit different. I'm going to come down here and cross through -5 like a line, like a linear root. Turn a little bit sooner so that I can approach to the left of 3, so that I can turn at 3, and then decrease like that. There's F. Y-intercept is going to be totally different because of the placement of the exponent. F of 0 is going to be -4 times 5 times -3 squared. 20 times 9 is -20 times 9 is -180, I think. -180. There you go. Okay. I've been doing good curves. Let me show you what not to draw. Don't draw like that. Don't have this get lazy and dip in that direction. We know the differences. Don't show that property. And don't draw it linear. So just draw curve more or draw less. Don't go in that direction. Okay. Do label the curve. Make sure that you are always curving. I mean, I guess could tackle a cubic root, but we've already seen a cubic root. Just real quick here, if I give you y equals x minus 3 all cubed, this is a degree 3 polynomial function with a positive leading coefficient. So write positive n behavior, opposite n behavior. But this cubic only has one x-intercepts. Because of their opposite n behaviors, cubics must have an x-intercept. This root is going to be a cubed root. So the curve looks like cubic root, sorry, maybe cubed root isn't the best term. Yeah, the function looks like a cubic near x equals 3. It looks like y equals x cubed near x equals 3. Y-intercept f0 is negative 3 cubed, or, well, okay, negative 27. Now let's take a look at some quartics. Let's consider f of x equals x plus 5 times x plus 4 times x minus 1 times x minus 3. I see a degree of 4, x times x times x times x. I see a leading coefficient of positive 1. So I draw a polynomial function with right positive n behavior, and because of the even nature of the degree, I'm going to have similar n behavior. I draw a curve that has 4 x-intercepts because I have 4 factors with roots. A root of negative 5, a root of negative 4, a root at positive 1, and a root at positive 3. And I try my best to draw a smooth curve. Now this curve is going to point something out to you here. You should sort of notice this organically without me telling you. Make sure that you do this. Notice when your x-intercepts are closer together, you have less time to dip down. When your x-intercepts are a medium distance together, you have more time to dip down. And when your x-intercepts are further together, you have more time to change. Right? So this distance, I was going to say amplitude. It's not really an amplitude. That distance there is the largest distance. This one is the second smallest. This one is the smallest right there. Okay. You'll feel that happen on your own when you draw a smooth curve. Y-intercepts are going to get larger for when you have like 4 factors. Yeah, let's see. We could probably just, I don't think you have to show your substitution. It's going to be 20 times 3. So 60, positive 60 seems to match my prediction about the end behavior. Okay. With quartics, you can get some pretty cool shapes, and higher ordered functions can have even more interesting shapes. We'll try something higher ordered the next day after this, the next lesson after this. Here's a degree 4 polynomial function. Don't expand it. What would you do with standard form? Would you read the leading coefficient and the degree? Well, the degree you can see. You're going to have x times x times x times x. There's going to be an x to the exponent 4 here, and your leading coefficient is going to be 1 times 1 times 1 times 1 times negative 1. I mean, I don't even think you should write this out, but the other thing that students sometimes use, especially for quadratics in grade 11, is they expand to get the constant term to find the y-intercept. You can always find the y-intercept by just substituting in x equals 0. There's no need to expand yet. Leading coefficient is negative, so write negative n behavior. Degree is even, so similar n behavior. This degree 4 polynomial function has only 2 x-intercepts, and one of the ways that can happen is by having a cubic root and a linear root. Now, when I aim for a cubic root, I didn't point this out on the other page, you want to aim even further to the left from the root so that you have time to exaggerate the horizontal nature. It's almost as if, here, let me draw a linear root. For a linear root, you just aim right for the root and you crash right through it. For a quadratic root, you need to aim a little bit so that you have time to turn, like a little bit to the left, so you have time to turn and bounce off of it. For a cubic root, It's like you're coming in for a landing. You're dive bombing. You're a bird dive bombing. And instead of crashing through or swooping up the fish and then going back up, you're coming in for a landing. So you kind of want to level out pretty soon so that most of your velocity is horizontal instead of vertical. Okay, so as your order increases, you tend to aim a little bit more to the left of the x-intercepts so that you have time to bend. Let's curl up like this, and then I know I need to crash through at 2 like a line. So I'll go crash. And look at that. I missed my x-intercept. What am I going to do? Am I going to get some white out and draw over this? If I'm working in pencil, would I erase the curve? You could do those things, or you do this. You say, you know what? I'd like that to be 2. Now, I can't make 2 over here, but I can 2's where I say it is, just like the y-intercept is going to be where I say it is. Y-intercept f of 0 is going to be negative 4 cubed. Sorry, the opposite of 4 cubed. It's going to be the same thing as negative 4 cubed. Times negative 2. What's that? 16. 64, negative 64, positive 128. There you go. 128. Let's try one more, just to check and see if we're accidentally taking the opposite of those. There's no thing, sometimes students call questions like this a trick question. There's no trick here. It's checking to see if you understand instead of memorize. We'll see some students draw a curve with x-intercepts of negative 3 and 3. Maybe because they've been told, they were given a reference sheet that says with x minus p times x plus q, or x minus s times x plus t, those are your x-intercepts. Or they've noticed that sometimes it seems to be that the x-intercept is the opposite of that number. No. My leading coefficient here is technically, its value is going to be 2 squared times 2 squared. There's going to be a 2x times a 2x times a 2x times a 2x. My leading coefficient is positive 4. My function in expanded form would be positive, 16. It would be 16x to the exponent 4 plus blah, 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 blah. Okay. All I really care about is the fact that positive, positive, even positive, it's going to be, my leading coefficient is positive. Right, positive, and behavior. I also care about the fact that this is going to be a degree 4 polynomial function. 1, 2, 3, 4. Meaning I have similar end behavior. My x-intercepts, or my roots, occur at the roots of the factors. F of x will be equal to 0 when 2x minus 3 is equal to 0. That happens when x is 3 halves. Or when 2x plus 3 is equal to 0. That happens when x is negative 3 halves. That's interesting to see, or to tell, during COVID when students were like using technology when they shouldn't have, because they'd put 3 halves close to there. Or maybe sometimes students think, oh, 3 halves is a small number, so they put it there. I mean, you're just zoom in so that you can see where 3 halves and negative 3 halves is. Okay. And draw a curve that bounces off the axis at negative 3 halves and bounces off the axis at positive 3 halves. Because of this symmetry in the order of these factors and the symmetry in the distance here, this curve will have a local maximum on the y-axis. It should. Just make my y-axis a little bigger and hope nobody notices. Whatever. You're not responsible for that behavior. Label that y-intercept. F of 0 is going to be 2 times 0 is 0, minus 3 is negative 3, squared is going to be 9, times 2 times 0 is 0, plus 3 is going to be 3, squared is going to be 9. So 81. I'll label that 81. Okay. Focus on appropriate curvature, but also work on efficiency. Not necessarily speed, but efficiency. Some people need more time to do things, but if you're taking 10 minutes to draw this curve because you're doing a table of values, you're not demonstrating the level of understanding that we're looking for in this course. Try out your worksheet 1.9.1. Desmos can help you check. There are also solutions on our course folder, as always.